Now we're back into the circle trig, and we're going to do another example where we find the sine and the cosine using the unit circle. And this time of pi over 4 radians or 45 degrees. I did want to comment that in the previous video I talked about how when we think of a value t as a real number, how we can use that value t not only on a number line, but we can also think of it as the measure of an angle. Because if I use, for example, the one I'm going to do for this problem, if I use this unit circle and I have this distance here being t, now when I say a distance, I mean the arc length being t here, we know that arc length is equal to the radius times theta. So if I'm using the unit circle, you can see then that the radius would be 1 and that the arc length would equal the angle. Again, I'm trying to emphasize that when we use radian measure, as compared to using degrees, we can line it up more with the real number system. And you'll see that when we get to the graphs a little bit more, but I want you to keep that in mind, that this distance and the measure of this angle in radians are going to be the same, as long as it's a unit circle. Now let's go back to this guy. I tried to draw him so he looked like a 45-degree guy, and I think I did an okay job. I'm going to drop a perpendicular here, and because this measure is 1 and this is pi over 4 or 45 degrees, I have a 45, 45, 90. Each leg will be the length of the hypotenuse divided by the square root of 2, which is the square root of 2 over 2, if you write that in simplest radical form. So this is the square root of 2 over 2, and this is the square root of 2 over 2. So this point right here would be the point, the square root of 2 over 2, the square root of 2 over 2. And since we're asking you to find the cosine of pi over 4, that's the x value, and the sine of pi over 4, that's the y value, notice that they're the same exact value. Now if you looked over here and you saw this big chart of values, and I had a couple of blanks here because I wanted to put those in, that the cosine is the square root of 2 over 2, and that the sine is the square root of 2 over 2. These are all multiples of 30 and multiples of 45. The multiples of 30 are in the blue, the multiples of 45 are in the black. And these are the equivalent radian measure from 0 to 360 to 2 pi. And these are the sines and the cosines of those angles. Now, we can find each one of these by drawing a right triangle like I did here, because these are all going to be special right triangles. However, you will discover you will save a lot of time if you just try to put these to memory. This is what I was talking about in the previous video. Try to put these to memory because they happen so often in the course of working problems, solving equations involving trig functions and such, that it's worth the time and effort to take the time to memorize it. Now, when I taught in a more traditional classroom, I would give my students timed quizzes where they would be giving 10 angles, some of the angles in degrees, some of the angles in radians, all mixed up, not in order. And they had to give the sine or the cosine of them. And it forced the students in a traditional classroom to eventually memorize those values. And there's patterns and such, and there's probably half a dozen YouTube videos that'll show you some little shortcut. But you can see that the numbers are essentially the same numbers. They're either 1, 0, square root of 2 over 2, square root of 3 over 2 or a half, or they're opposites. And those are the only values. So if you can practice memorizing these for sine and cosine, we can do it for tangent. We can figure out tangent because tangent, remember with the unit circle, is y over x. So it would be the sine of the angle over the cosine of the angle. And if we know the sine and the cosine, we can find that out, as well as the other three trig functions. So it's useful to keep track of the SIGN sign when you're talking about finding the sine, the cosine, or the tangent, or any of the other trig functions when you're looking at angles that are in standard form. So I've drawn a set of axes here, and I put down ordered pairs not based on numbers, but based on their SIGN sign. We know any ordered pair in the first quadrant, the x value is positive, the y value is positive. In the second quadrant, the x is negative, the y is positive, and so all the way around, right? Well, remember, the cosine's the x, the sine's the y. So this tells me that the cosine's positive and that the sine is positive. All right, so I'm going to put an A there. Okay, the A actually stands for all possible trig functions here. They're going to be positive if it's a first quadrant angle. First quadrant angle, it means when the angle is written in standard form that the terminal side is in the first quadrant. That's a first quadrant angle. A second quadrant angle is an angle that's when written in standard form, standard position I should say, that its terminal side's in the second quadrant. Third quadrant angle, fourth quadrant angle. If it's right on one of the axes, then it's not a quadrant angle, it's called a quadrantal angle. But in this case, both of these, the sine and the cosine, are going to be positive, which means the tangent's positive, which means the other three are because they're reciprocals. So they're all positive here. Over here, the cosine is negative, the sine is positive. So I'm going to put an S here for sine, that the sine is positive. And then down here, the sine and the cosine and the sine, I should say, are both negative in the third quadrant angles. But since tangent is sine of the angle over the cosine of the angle, a negative over a negative is positive, so I'm going to put a T here for tangent. Tangent's positive there. And then over here, I'm in the fourth quadrant, again in standard position in the fourth quadrant, terminal side, terminal rays in the fourth quadrant, standard position. The x is positive, the y is negative. That means the cosine is positive, the sine is negative, so the C for cosine, because it's positive, I wanted to put down the positive ones. So they're all positive here, the sine's positive here, the tangent's positive here, the cosine's positive here. ASTC, and an easy way to remember that is right here. All students take calculus, ASTC. All students take calculus. Because you're going to want to keep track of your SIGN, sine, SIGN of your sines, your cosines, and so on. Now, when we have a couple of angles, and I put two angles here in radian form, and this is negative 3 pi over 4, and this is positive 5 pi over 4. Now, I'm not going to be able to draw it exact, but negative 3 pi over 4 in standard position, well, of course, the initial ray goes this way, and it goes this way. 3 pi over 4, if it helps you, is 135 degrees, so this would be negative, so clockwise, and I would get negative 135. I'm just going to put 135 in here to remind me. Well, 5 pi over 4 in standard position, if I wrote that angle in standard position, again, initial ray this way. Here, I'll put this in a different color here, initial side right here. But it's, now 5 pi over 4, if you need to, you can look up here, 225 degrees. That would be counterclockwise, and look where I end up at. I end up with the same terminal side, the same terminal ray. So therefore, as I think I've mentioned before, these are coterminal angles. Coterminal angles are any two angles when in standard position have the same terminal side. Okay? The nice thing about coterminal angles is even though that the angles are different, these are clearly different measures. This is negative, this is positive. They're not equal. They're sines, they're cosines, they're tangents. All 6 trig function values are going to be the same because they have the same terminal ray. It's going to intersect the unit circle at the same point. Now you're going to have to drink that one in because that's really key in finding some of these values. We're going to use coterminal angles a bunch. So kind of get used to that idea. Now, this chart, again, I took the time to go ahead and put this out. You can find this online, you can make copies of this, but you do need to start trying to remember it because, especially if you're ever taking a test where you're not allowed the access of a computer or something, or your phone, I mean, you're gonna have to remember these values. But I have written out the domains for all 6 of the trig functions, the sine, the cosine, the tangent, the cotangent, the secant, the cosecant. Notice because these bottom 4 here, when written in by the definition of the unit circle, remember this was y over x, this was x over y, this was 1 over x, this was 1 over y. You've got a variable in the denominator, so you have to exclude all those angles that give you a 0 in the denominator. For example, pi over 2. If I'm trying to find the tangent of pi over 2, that's y over x, that's the sine over the cosine. Well, pi over 2, look right here. That's the sine 1 over the cosine 0. You can't have 0 in the bottom. So we omit pi over 2 plus all, this is what this is mean, all multiples of pi, all integral, k is an element of the integers, all integral multiples of pi that would be added on, because that would give me a bunch of, not only coterminal angles, but a bunch of other angles that would be undefined, that would give me a 0 in the denominator. Very similar for the breakdown here. Notice that these two have the same domain, and that these two have the same domain. Now this is the old-fashioned set builder notation. You can write this in interval notation, but it's a whole bunch of intervals. So one way to do this for tangent and for secant would be to say pi over 2 plus pi k, comma, 3 pi over 2 plus pi k, where k is an element of the set of integers. So that would give you all the different between pi over 2 and 3 pi over 2, between 3 pi over 2 and 5 pi over 2, between 5 pi over 2 and 7 pi over 2, and so on. Similarly, for 4 and 6 here, for cotangent and cosecant, this would be a way to use interval notation to write the domain here. This would be all multiples of pi here, all integral multiples. Notice that this is one more than this, so like if k is 0, this would be from 0 to 1 pi or pi. And if k is 1, this would be from 1 pi to 2 pi, from 2 pi to 3 pi, and so on down the line. It's a little weird, and you guys might need a little bit of time to kind of think about that one and try to practice getting to understand what it's meaning. Now, I want to evaluate the 6 trig functions of the real number t. Now notice here, it says real number t. It doesn't say the angle, it says the real number t, because the real number t back here, remember, is going to match up with the angle in radians. And notice that in both of these cases we have the angles written in radian form here. Because even though it says it's a real number, this is going to be my theta in terms of radians. So I'm asked to find the sine, the cosine, the tangent, the cotangent, the secant, the cosecant, all 6 trig functions of negative 2 pi. Well, let's think about this. I don't have negative 2 pi here on my chart, but if I was to add 2 pi to this, I would get a coterminal angle. Now think about what negative 2 pi looks like. Negative 2 pi would be 1 revolution around this way. If I add a 2 pi to it, I'm going to get it 0. That's going to have the same terminal side. They're going to be coterminal angles. You can find coterminal angles by adding on 2 pi or 360 degrees to the angle. And a little different for the tangent and the cotangent, because of the way they repeat every 180 degrees or every pi radians. So we would add on multiples of that. But in this case here, if I add on 2 pi, if I add on 2 pi to this, I get 0. So I'm going to say that the sine of negative 2 pi is equal to the sine of 0. Now I'm not saying that negative 2 pi is equal to 0. I'm saying their signs are the same. And then if I need to, I can look up here. I can see that the sine of 0 is, find it right up there, 0. The cosine of negative 2 pi would be the cosine of 0, which would be 1. I'm going to find the tangent of negative 2 pi, which is the tangent of 0. Now remember, tangent is sine over cosine, so this would be 0 over 1, which is 0. So all 3 so far are so good. Now I'm going to do the cotangent of negative 2 pi, which is equal to the cotangent of 0. And the cotangent of 0, remember that's x over y, that is your cosine over your sine. Well, I'd get a 1 over 0. So I'm going to say not equal to undefined. I'm going to say that this implies that it's undefined. Because you can't divide by 0. Division by 0 is undefined. And now I have 2 more. I have the cosecant of negative 2 pi. And I have the secant of negative 2 pi. The cosecant of negative 2 pi is the same as the cosecant of 0. Now remember, cosecant and sine are reciprocals. So it's the reciprocal of 0, which would be 1 over 0. So once again, undefined. Now the secant of negative 2 pi is the same as the secant of 2 pi, or excuse me, 2 pi, add 2 pi is 0. And this will be, remember, it's the reciprocal of cosine. It's equal to the reciprocal of 1, which is 1. And I have those 6, well, I have 4, and then the 2 that are undefined. And I've evaluated those functions at that number. Now, for 3 pi over 2, there's really nothing wrong with this guy. He's not negative. He's not too big. I like my angles, if possible, to be between 0 and 2 pi or 0 and 360 if I'm doing degrees. And I'm going to find the sine of 3 pi over 2, the cosine of 3 pi over 2, the tangent of 3 pi over 2, hope I left enough space, the cotangent of 3 pi over 2, the secant of 3 pi over 2, and the cosecant of 3 pi over 2. Okay, well, the sine of 3 pi over 2, check your table, 3 pi over 2, right there. The cosine is 0, the sine is -1, the sine is -1, the cosine is 0. Well, that's really all I need. Tangent is sine over cosine, so -1 divided by 0 is undefined. So again, I'm not going to write equals undefined, I'm going to say it implies that it's undefined. When you draw a double arrow like that, it means implies. The cotangent is the cosine over the sine, so it'd be 0 over -1, and 0 over -1 is 0. The secant of 3 pi over 2 would be the reciprocal of cosine. Well, the reciprocal of 0, it means it's undefined. So again, I make that implies that it's undefined here. And last but not least, the cosecant of 3 pi over 2. Now sine and cosecant are reciprocals, so the reciprocal of -1 is -1. If you memorize this table and you use coterminal angles to assist you, you can find sines and cosines and tangents and all the rest of them for all multiples of 30 and multiples of 45, or multiples of pi over 6 and multiples of pi over 4 radians. And here's some examples. A lot of stuff in here that you're going to need to keep track of. So be sure to read through this, look through this, check out the notes, and make sure you feel comfortable with this before you go on too much further.